which I thought was conceptually the most difficult one, even though it wasn't mathematically the most difficult one, it's conceptually the most difficult one, right? Did you find that, Alex? Yeah, me too. I got it wrong the very first time I did it in 1982.
Did you read the page?
I read the page. I read the page a long time ago, Matt.
So yeah, we first looked at this page like, who the hell's going to read this?
So I know, it's complicated, that page. I'm reading, I mean, So the current density here grows linearly, right? It's positive and out of the board. And I'm not doing a very good job of representing that. The first thing you think, I'm going to show you my thinking behind this, okay? Because as you've heard me say this to you in this class and the other class, I'm not a picture thinker. I have to prove things with the laws mathematically. I just can't grab the thing and draw pictures of it. I'm not that kind of thing. If you are, great for you. But here's the first thing. What's the magnetic field look like? Forget the page. Okay? The page. Okay? We know this. We know if I were to draw an Amperian loop up here, and I'm going to draw it here. Okay? I'm going to draw it right here. Somebody remind me, this is what, X or Y?
Oh, that's Y.
This is Y.
The up Z.
This is, thank you. This is Z,
And
and X is out. The current density then, J is equal to J naught over A, magnitude Z I hat, right?
Yeah.
This is out of the board. Doesn't shift, it's out of the board.
Yeah.
Correct? Here's how I know, contrary to what I would think, that the current density, or rather the magnetic field, has a different sign above and below. Correct? You read the page. That's where you got that from.
Yeah.
Okay? Here's why I know that's got to be true. I'm going to draw my little Amperian loop. This is delta Y along here, minus J hat. This is delta X along here, and this is delta Y J hat, and this is delta Z, for goodness sakes, Z for Z. By symmetry, I immediately know nothing can depend on X and Y. Correct?
Correct.
The magnetic field here, if anything, have to cancel. There can't be any dependence along here. However, there is something this way. Because even though there can't be any dependence along X of the magnetic field, there can't be any dependence along Y of the magnetic field. That tells me, first of all, B is equal to B naught. Let's not use B naught. Let's just use B of Z.
Yeah.
Okay? Now the direction also, by the argument we just put that grad cross B has to give you something like this. Can't have any component in this direction. It could have a component in this direction, but because you'll find out if you do grad cross B, it can't. Also, that would break the symmetry of the problem. This can only be a function of Z, but it can't have a vectorial component that direction. It certainly can't have a vectorial component this direction, because any current, as we just saw with grad cross B is J, if the current's this way, my only two choices for the magnetic field are like this. Now, it could be up, but here, let me show you something real quick. Draw a little loop. Draw another little loop. Draw another little loop. What happens to that side and that side? One goes up, one comes down. One goes up, one comes down. You can't have any component this direction. Here's what I'm not going to tell you what confused me until I finish this problem. Okay, and I still remember being confused about this over 30 some years ago. Yeah.
One of the questions we were having when we were doing the problem is it was saying that it's BZ, but the B field is constant as you go outside of the loop.
Because it's an infinite sheet.
So when it's a circle, they say it's radially dependent. Like why is, because it's an infinite sheet and this circle isn't infinite. That's
right.
The
That's a localized thing.
Okay.
This goes on forever.
Okay.
So you keep adding and adding and adding and adding.
So if you go far
it's
away,
constant.
it's still the same.
It's constant.
But we're talking up in the Z.
Up in the Z.
Right, up in the Z. So, I mean, it's constant, it's infinite across Y, and it's
it's an infinite. The reason is you have an infinite source. Let me take the line charge, right? Lambda. And we integrated that and we got an electric field, correct? And that electric field did not fall off like 1 over r squared. The thing fell off like the natural log, which has a very, very extremely long extension. When we did when we did 2 wires, remember I said, look, we have to calculate not the force, but to calculate the force per unit length, because the total force is what? Infinite, right? You remember that?
Yeah.
That's the same thing happening here. It's an artificial situation. Can you ever have an infinite slab? So it diminishes. I should make you work that problem in the exam.
This
You
one
should
right
not.
here.
This one, okay. First of all, here's the situation. I got current coming out of here. So whatever I have, I know this. Whose law is this, Marquita?
By
No, it's amperes.
No, it's not.
Yes, it is. Yes.
No.
Yes.
No.
Yes.
No.
Yes. I'll be right. All right.
Shower just made up.
This here's and this is from very general considerations. Nick,
Oh
ready to
yeah,
leave,
because the
No,
new.
I'm digesting ICAT.
Okay. You'll
I've
be-
never heard that before in my life.
I expect
None
you
of
to be able
this.
He's like he's still high hat.
None of this.
Oh yes, the mu pi over 4 is pi over 4, and that's.
All right.
Okay, I'm getting there.
Before we do anything,
Yeah.
I'm not going to do any fancy math here. I'm not going to do any fancy math. I'm going to go right to the bisector. Go right in the middle. Okay? And I'm going to go this way, and I'm going to go this way. So I have by symmetry what's true about the magnitude of the magnetic field here. And the magnitude of the magnet, not the direction, the magnitude. They're the same.
Yeah.
So what I now say is V upper dot minus delta Y J hat. And how do I know it's my, well, because it's going to the left, right? I get no contribution from this, plus B lower delta Y J hat is equal to a number. I don't care what it is. I'm not going to calculate that. Whatever it is, you know what it is? It's greater than 0. Agreed? What's true about the magnitude of B upper and B lower? You just said it. They're the same. If they were in the same direction, I'd be violating Ampere's law. Because I have minus here and plus there. If both above and below, they were in the same direction, what would happen? I'd get 0, right? If, for example, suppose B upper pointed that way and B lower pointed that way. Then I'd have minus J hat plus, or J hat dot J hat, which is, what's J hat dot J hat?
1.
He said it.
You're like, I don't even have to ask anymore. You know, you just bam, right out. Yo, Marina missed it.
Wow.
Yeah, she missed one.
J
No,
cross.
you missed K hat cross K hat.
It happened, trust me.
She's giving me that evil eye.
I thought, last class you said you wouldn't harp on her anymore about that?
That's fine. I can take
I'm
it.
just a
I can take
known liar. All right. So this would be
You're welcome.
0. Good. Yeah, okay. J hat dot J. This would be 0 if they were in the same direction. Can't be. That immediately tells me what's true about the upper one. The upper one has to be in this direction. There's B upper. It's negative. And B lower has to be in the positive direction. Okay? Or I would get something less than 0 if I had it backwards. That immediately tells me B upper and B lower. Okay? Now I can use Ampere's law to find the functional form of it. The only thing in this problem, to me, this was the most complicated issue. Because my instinct tells, let me show you where, again, the confusion was for me. I would see this as an infinite bunch of wires. But you can't really do it that way because it's an infinite bunch of sheets. And I kept thinking, well, each of these wires does this. Above and below, right? So I kept thinking, well, all those cancel this way. You can make them squares if you want, it doesn't matter. I thought everywhere the magnetic field had to be that direction. But it's not, because you can't think of them as wires. This is really sheets stacked on top of each other. And the behavior of a long thing of sheets is a little more subtle than a bunch of wires side by side. Okay? A little more subtle. So we can get the answer now by drawing an Amperian loop. Why is it so good to draw a loop here? Why is it so good to draw a loop right in the middle? Well, first of all, that's Z equals 0, correct?
Yeah.
What's the magnetic field on that line?
0.
0. That helps. What's the magnetic field on this line? 0. What's the magnetic field on the line? That's what we're getting on the outside. You want to do the inside first or the outside first?
Outside.
The outside gives me B